Entropy versus cross entropy. In machine learning, many times you would surely have heard this term entropy. Along with this, maybe when you're learning loss functions or something, you would have heard about cross entropy as well. For example, you would have heard about binary cross entropy, or maybe categorical cross entropy, or sparse categorical cross entropy. While learning these things, surely you would have thought of what exactly is this cross entropy? What is meant by cross entropy here? So this is what this lecture is for. We are going to see what exactly is entropy, what exactly is cross entropy, and what is the difference between entropy and cross entropy. First of all, let us clarify what is entropy. Entropy, it is the uncertainty of an event or a distribution, or in another words you can say this is the average information that is inherent in a random variable's possible outcomes. This is another way of seeing entropy. What we'll see is what I told us, it is the average information inherent in a random variable's possible outcomes. So let us see what is average information here. Information, we already learned this in the previous lectures. Information gain, let us say, corresponding to some particular random variable xi. So let us consider there is a distribution P, and this P is over events, let us say x1, x2, like this. These are the events over which P is distributed. If this is the case, then taking any particular event from here, the information gain on that event, this can be written as minus log P of xi. So this is a way of writing information gain. How can you understand this information gain? One way of seeing this is the number of bits that you will need to encode this particular event xi if it is occurring. That is one way of understanding it. And from this automatically you can understand that whenever an event is a rare event, that is whenever it has a lower probability, the information gain will be higher. The same way, if it is an event which is a very common event, something which is having very high probability, it is supposed to occur, then in this case, information gain will be lower. What is the reason? Let us say I am giving you an event which you never expected. Then this event will actually surprise you. That means you got a lot of information from this particular idea that I gave, or the information that I gave. So you gained a lot of information. That is why information gain is higher. For example, let us say I'm tossing a coin. Okay, I tossed a coin. It is expected that either heads or tails will come up. But let us say I'm telling you that when I tossed a coin, it is a flat surface, and what came up were not either heads nor tails, and the coin landed like this in the middle. So this thing actually had no probability at all. According to you, 0.5 probability is for heads and 0.5 probability is for tails, and there is 0 probability for a coin to land like this. But if I am coming and telling you that the event for which you gave 0 probability, which is the coin not landing on heads or on tails, but instead staying like this on the floor without landing on heads or tails, this particular thing gives you a lot of information because it surprised you. You never expected this. Or let us say there is a football match going on or a cricket match going on, and it is between, let us say, India and some smaller nation, let us say something like Kenya maybe. Then generally you are expecting that India is going to win this match. But if someone comes and tells you that Kenya managed to win this match, then information gain is much higher because probability of India winning was much higher according to you, and probability of Kenya winning was way lower. This is why when someone comes and tells you, hey, Kenya won this match, that means you gained a lot of information. So this is why information gain is always larger for an event with lower probability, and always information gain is lower for an event with larger probability. Next thing is entropy. I told you is the expected information. So entropy H of P, this can be written as expected information. This is with respect to distribution P. Okay. Expectation of minus log P of X. This can be written as expectation. We already learned in very initial lectures itself. Sum over all the I, P of Xi log P of Xi. So this is the expectation. This is what you will call as entropy of the event. How should you understand this particular term, entropy? This is uncertainty that is associated along with this particular event itself, kind of self-entropy. That is how you should understand this. So then the question is, what is cross entropy? One more thing, in terms of these bits, how can I explain this entropy? I can say it is the average number of bits that are needed to encode an event in P. I have this distribution P. If I want to encode an event that is present in P, then what is the average number of bits that I will take when I'm using a code that exactly matches distribution P? This is what entropy is all about. It is average number of bits. This is how you can understand. Information gain is number of bits required for that particular event. If you have this complete distribution, then for any event, average number of bits required in order to encode that is what you will call as entropy. So you can somewhat see it as average amount of uncertainty in this distribution. This is the simple way of understanding. Next thing is, if that is the case, then what is cross entropy? Considering that you already understood entropy, then what is cross entropy? So cross entropy, the same situation. Let us take the same situation where you have distribution P. I told you that entropy tells you the number of bits that are required when you are having P and you are having a code which is optimized for P, then average bits required to encode an event. This is what entropy means. So cross entropy, it measures how well, let us say you have a predicted distribution Q, then how well does this Q approximate true distribution P? This is how you can understand cross entropy. Or if I explain in terms of the bits that we saw entropy in, then this will be number of bits that are needed to identify an event from set of possibilities if the coding scheme is made for, this is the most important part, that my coding scheme is made for distribution P. This is the important part. But my true distribution is, coding is made for distribution Q, but my true distribution is P. This is the case. In this case, normal entropy, coding is also for P, true distribution is also for P. Then what is the average number of bits required? But coming to cross entropy, coding is done for Q, which is a different distribution, but I am trying to approximate P using Q. Then if the code is prepared according to Q, then for encoding events in P, what is the average number of bits required? This is the concept of cross entropy. Then when will cross entropy become lesser? Cross entropy will come closer and closer to entropy whenever your Q is almost the same as P. Because what are you doing? You want to encode the events that are there in P. But for some reason, you are not using the code for P, but instead you are using the code for another distribution Q. So when Q is very similar to P, then what happens is average number of bits required to encode will be same as what would have happened if you use the code for P. That is, if you use the code for P itself, that is just entropy. Cross entropy is when you use code for Q, but if Q is very similar to P, then the average number of bits required will be same as that what you used when code was made for P. So this is the major difference between entropy and cross entropy. So how can you write formula for cross entropy? We already learned about this in previous lectures, but still this formula, it will be sigma I P of xi log Q of xi. So this is where it is different. So this entropy, one more thing, One more thing, the difference between this cross entropy and entropy, this is the KL divergence that we learned. So how can you interpret this? That is, this difference will tell you how inefficient is your code, because you made the code for Q instead of P. And now if there is a difference between this and entropy, that will somewhat tell you how inefficient is your code. Okay, so this is how you can understand my H of PQ, which is my cross entropy, minus entropy. This will give me the KL divergence. This will give me KL divergence of Q from P. This is what KL divergence is. So once more, what exactly is cross entropy? You can see it like this: the cost of describing true distribution but with a different distribution. You're actually having P, but you want to describe it using Q. Then what is the cost? This is what cross entropy is all about. Okay, so that is the difference between entropy and cross entropy.